Hi guys, I'm Daimayan. I'm the machine learning engineer and content creator all over social media, and newly one of the content creator of ProjectPro. So I hope you enjoy to see me. And in this video, I want to talk about neural networks, its mechanism, its mathematics, and I want to implement it in C++. Probably I will implement in the second video of this video series. So let's start with this question to this video. How do we learn? What is learning? How do we distinguish that one object is a table and another object is a pen? How do we recognize pen? We have been looking for answers to many questions like these for a long time under the name of the philosophy of artificial intelligence. Plan to make a nice video where I want to explain the philosophy of artificial intelligence at a later date, so subscribe to now and so don't miss it. So back to the question, how do we learn? What we call learning is actually reaching the general solution of a problem and recording this general solution in our neurons. Eventually, when information comes into our brain, we consult our neurons and solve it. Yes, of course, there's a lot of more than that, and that's too abstract. Let's explain it a little more. Since we are a baby, every kind of information that comes into our brain leaves a trace in our neurons. And the information coming to our neurons through synapses changes as a result of these previously left traces. This process of change is actually the very process of what we call interpretation, what we call intelligence, what we call learning, what we call thinking. Of course, I I call it a trace, but it's not a trace, it's a gateway that strengthens or awakens the chemical electricity. In other words, our neurons give the incoming information an evaluation rate according to where it comes from. For example, neuron A considers the information coming from neuron C more important and strengthens the signal coming from it. Why? It weakens the signal coming from neuron B. And this neuron A checks whether the sum of the signals coming from the neurons it is connected to, such as neuron B and C, is greater than a threshold value. If it's larger, the neuron fires. If it's smaller, neuron does not fire. These are all hypotheses that were proposed in the 40s and 50s to explain how neural networks work. Neural networks in computer science were developed around these hypotheses. So, what is artificial neural network? To get started, I will explain a type of artificial neuron called perceptron. Perceptrons were developed in the 50s and 60s by scientists from Rosenblatt, inspired by early work of Warren McCullough and Walter Pitts. A perceptron, several inputs such as x1, x2, x3, and produce a single binary output. That there's a weights, weight 1, weight 2, weight 3, and blah blah, real numbers expressing the importance of the respective inputs to the output. The neuron's output, 0 or 1, is determined by whether the weighted sum of weight multiply inputs is less than or greater than sum of threshold value. Just like the weights, the threshold is a real number which is parameter of the neuron. To put in more precise algebraic terms, we get this. Cumulative sum of weight multiply inputs bigger than threshold, we get 1. Smaller or equal to threshold, we get 0. That's all there is to how a perceptron works. That's the basic mathematical model, and a way you can think about the perceptron is that it's a device that makes decision by weighing up evidence. Let me give an example. It's not a very realistic example, but it's easy to understand, and we'll soon get more realistic examples. For example, in implementation, suppose the weekend is coming up and you have heard that there's going to be cheese festival in your city. You like cheese, you adore cheese, and are trying to decide whether or not to go to the festival. You might make your decision by weighing up 3 factors. Is the weather good? Does a boyfriend or girlfriend want to accompany you? Is the festival near the public transit? You don't own a car, so you use the public transit. We can represent these 3 factors by corresponding binary variables x1, x2, and x3. For instance, we'd have x1 equal 1 if the weather is good, and x1 equals 0 if the weather is bad. And we can do the same for other inputs. At this point, if I make threshold 5 and give the weight of good weather 6 and weight of the others 2. Regardless of the other condition, if the weather is good, here we go. If the weather is bad, you don't. By changing the threshold and weights here, we can come up with different decision mechanisms. Instead of using threshold, if I move to the other side of the equation and call it a bias, then I can look at whether the output of the neuron is greater than 0, not whether than is greater than the threshold, and decide whether the neuron fires or not. If it's bigger than 0, it fires. If it's smaller than 0, it's not. Activation function we see in there. So activation function, what is activation function? An activation function is a function that is applied to output of neuron in a neural network. It determines whether the neuron should be activated or not based on the input signal. Activation function also determines a non-linearity to the neural network, which allows it to learn complex patterns from the data. There are different types of activation functions, such as sigmoid, such as ReLU, such as linear ReLU, such as softmax, etc. Each activation function has its own advantages and disadvantages. For example, ReLU is more useful for deep learning, and every activation function can be used for different purposes and scenarios. I will explain that now in the paint. So actually, the neural networks, what we do in the neural networks, what we're gonna try. So actually, let's example for abstract way. Let's we define equation, for example, like this. Yeah, I draw very bad. Yep. So x1, so let's say x1, x2, x3. We know the x1, x2, x3 actually, isn't it? But we don't know A, B, C, and D term. D is actually, if we say this is the output, it should be the output, equal to output, isn't it? But I moved the output at the other side of the equation, so D is bias negative minus output equal 0. So actually, the weights are A, B, and C in the neural network, and D is bias minus output. So I find the biases and weighted for generalize to equation. If I'm generalize the equation, I can solve every possible inputs with this equation. For example, if I'm find the weights such as 6x1 and 2x2 plus 2x3, and let's say the bias negative 5 equal 0. So this is the conflict. We shouldn't say equal, because it's now is not a equation, is a neural network threshold check. So we should check is bigger than or smaller than 0. So in this example, which we take before, let's say x1 is 1, so weather is good. x2, no, you don't have a girlfriend, so it's not coming to you. So it's 0. x3 is okay, 1. There's a public transit near to you. And let's calculate 6 plus 0 plus 2 minus 5 is equal to 3. So 3 is bigger than 0, so neuron fires. Actually, we find the general solution of equation. We find the coefficient of the equation. So actually, activation function is so important in this area, because if you look the equation, this is linear equation. So in the real world, every problem is linear, mostly is not. So the activation function is so important actually in this solve the most problem is learn everything to with neural networks, to train neural networks for more complex data. So I pass this patch. This is the some equations we talked about before. This is the vectorized schematic, and we add the bias in terms of cumulative sum multiply weight, weight multiply inputs, and activation function in here probably sigmoid. So this is the forward propagation. That's mean we give the inputs to the neural networks and we get the outputs. That's mean the forward propagation. So I give these inputs to the neural network with this weights and summing up with and put the sigmoid function and I get the outputs. This is the forward propagation. Actually, this is the run cycle of the neural network. But learning is not with the forward propagation. If I want to learn, if I want to train a neural network, what I use to learn every time? If I want to train a neural network, I initialize the randomly weights and biases with neural network and forward propagate it. I get the outputs. Afterward, I use the backpropagation for training. For example, I use the calculation example in there. So I have the data, for example, 200 kilometer is speed actually. And I don't know, what is this? And the autonomous, is it autonomous or not? And the output layer is best, good, average, and worst. If it's best, it should be 1. In this particular example, is the best class, so it's 1 and another's is 0. And I talk about the normalization in there. Actually, normalization is too important in neural networks because if you look the data, speed of more and more higher than autonomous or not, because autonomous or not is equal to 0 or 1, isn't it? But the speed, it can be a 300 kilometer, it can be a 250 kilometer. Yeah, it should be more higher. That's why I should normalize the data between 0 and 1 to more precise training. And with this training, I get the output with the forward propagation. I get the output layer values, isn't it? So with this with this particular example data, I get the output layer such as 0.6, 0.7, 0.3, and 0.1. But the true output should be best is 1, the another is 0. So the neural networks didn't find the best solution for me. This is error. This is what we call error. So error of the to the output neuron is equal to the true output of the neuron minus output of the neuron. So in the best class, true output should be 1, but the actual output is 0.6. So the error is 0.4. For the second one, minus 0.7. So the third one, minus 0.3. For the last one, minus 0.1. This is the error for the output layer. So if I'm calculating the errors, what I should do? With these errors, I should updating this weight because the training is learning the weights. If I find the best weight and biases for neural network, I trained. So let's see how we can updating weights between hidden and output layer in there. So changing amount of the G to the hidden neuron and M to the output neuron. So in this example, if you can see the G to the output hidden layer neuron and M to the output neuron in for this example. This is the learning rate given by users. This is the value of the neuron. T is iteration. Why we should use the iteration? Because this is the changing amount. So if I'm using the iteration to find current weight, so this is loss of the amplitude output neuron. So I find the loss of the output neuron, such as activation function derivation. This is derivative of the activation function, and multiply error of the amplitude output neuron. And finally, we get the weights in G to the hidden layer neuron at current value of this weight plus changing amount of this neuron. So let's see in the example, I set the learning rate 0.5 and I write the equation which t iteration weight which we calculate, and current amount of weight is the 0.4, and I should find the changing amount. How can I should find the changing amount? Learning rate multiply loss of the neuron multiply current value of the neuron. So changing amount 0.5 is the learning rate, and when I'm trying to get the loss of amplitude neuron is equal to current value of the output neuron is 0.6 multiply the derivative of the activation function, which is 9. So this is the neuron error of the neuron, and multiply error of the neuron, and we get the 0.096. And I set down in the position here, and we multiply the value of the current neuron is the G to the hidden layer. So I get the changing amount of the weight is 0.039. So for the calculating t iteration weights, so previous weight is 0.4 plus 0. Changing amount of the weight is 0.039 is equal to t to the iteration new weight of the G to the hidden layer. So we calculate the hidden layers and output layer weights with that, but there's more than that, because there's an input layer and hidden layer here, and there is a weights here. So I have to calculate these weights too. So with calculating between input layer or previous hidden layer, yes, it can be more than one hidden layer. So updating weights between input layer or previous hidden layer and hidden layer, updating the weights, it should be influenced by the error of all outputs to output layer. This is so important for updating for input layer between hidden layer or hidden layer between hidden layer weights, because calculating this neuron loss, it should be the every output neuron connected to this neuron. So I should use the cumulative sum here to calculate the loss GTD neuron of hidden layer to calculate its loss for every output loss. So we should use the cumulative sum of the error, the outputs with coming from this neuron, and multiply by the weights to calculate this neuron whole output, all loss. When we're going to implement this in C++, you get a more understand this equation, because when you're looking at this mathematical equation, yeah, this confused a little bit, but in the coding, we more understand how we can do. So that's it for mathematical equations today. When implementing in C++ from scratch, we talk about more for these equations with how we implement it. Probably you will understand more in the step. So I think it's enough for this video. Thank you for watching. Thank you for being here. If you like the video, hit the like button and subscribe to the channel. If you have any question in your mind, please comment down below. I try to answer it if I see it. So thank you. See you in the next video.